Good day. I am Vincent Wolzinski, the Deputy Dean of the Yale School of Engineering and Applied Science and the James S. Tyler Director of the Yale Center for Engineering, Innovation, and Design. It's my honor today to speak to you about the concept that we call the Y-shaped engineers. Engineers that have breadth within social studies and the humanities, depth within the engineering discipline, and they use these skills to apply them to problems of purpose. That is supported through 4 initiatives. We'll begin by looking at the infrastructure that builds Y-shaped engineers. The Yale Center for Engineering, Innovation, and Design is our academic makerspace, an area on campus where faculty, staff, and students from across the university assemble to design and create. The CEID consists of a lecture space where we hold classes. That space is directly connected to an open studio. In the studio, students and others gather to pursue class projects associated with clubs, and their own interests, which might extend into entrepreneurship. They're supported with tools, hand tools, traditional machining tools, and rapid prototyping tools. In addition, we have a wet lab for the exploration of biological and chemical interest. Key to the CEID is not just this infrastructure, but also the programming, ranging from informal activities to more formal gatherings. We conduct this programming along the continuums of learn, make, share. We'll explore the make continuum. The most informal use of the CEID is to make use of the Open Studio, which is available 24 hours per day, 7 days a week. Students come in to pursue their own interests, perhaps get ready for the holidays, or participate in one of our workshops, such as chocolate making. The next level of formality is the support that we offer to our Yale engineering teams that build robots, teams that leave campus and go to other areas of the world, including Cameroon, where using the Engineers Without Borders project, build fresh water systems for villages in need. The most formal aspect of the Make Continuum is our summer fellowship. Here, Yale students spend the summer with us pursuing their own design interests. This last summer, David and JR, who are both rising sophomores, worked on a project for the United Nations and the government of Colombia. Citizens in Colombia designed 3 new forms of a face shield that could be integrated with a face mask to reduce the spread of coronavirus. JR and David studied these face shields using computer-aided design and flow simulation. What they did was examine the particle flow as you would exhale and also inhale, providing their results to the United Nations and Colombia to advance this project within that nation. As another example, Maria worked with the Metropolitan Museum of New York. The sarcophagus that held ancient mummies was found to be deteriorating. So Maria worked with members of the museum to understand that problem. She modeled the platform upon which the sarcophagus was placed and then used that model to construct its analog version within the Center for Engineering, Innovation, and Design. Then using the principles of engineering, including vibration analysis, she designed a spring damper system. First, in the digital world, understanding its operating principles and effect on the sarcophagus, and then manufacturing that device and testing it on the platform that she had built. Perhaps the most formal form of learning that takes place within the Center for Engineering, Innovation, and Design is in our courses. We offer courses over a range of topics, including medical design, sustainable design, design of new products, and design for new students. During that first year design class, we partner the students with individuals at Yale who need a technical solution. In one example, the curator of a new exhibit at the museum asked for the help of the students. The exhibit was one of displaying ancient Chinese mirrors. And the challenge for the students was to create a mechanism where visitors would not only see these mirrors hanging on the wall, but able to experience them by touching them, by feeling them, by looking at them. The students began their pursuit by digitizing one of the mirrors. And once that mirror existed in the digital world, they could use the tools within the design center to reconstruct it in the physical world. In this case, using CNC machining to machine the same composition of bronze that the Chinese had used 3,000 years before. And in the end, they were able to create a replica. And once the replica was created, they could replicate that and create additional artifacts. An additional challenge for the students was to duplicate the aging process. So they created a formula that caused the bronze to age, such as in the end, they had a tool that could be passed along to the museum visitors and also a display that showed how these mirrors changed with time. In this case, we see engineering working hand in hand with the arts.
Michelangelo's David, strong, youthful, standing tall throughout the centuries. But the standing is becoming a problem.
Over time, David has started tilting forward, and so that's creating hairline cracks in the back of its ankles. The sculpture is probably, in a couple centuries, going to fall over.
Michelle knows all about this because she and her fellow students built a way to study it in an introductory engineering class.
Each group gets assigned their own project that helps someone at Yale with the problem that they have.
Michelle's group worked with Yale's Institute for the Preservation of Cultural Heritage, known as the IPCH, which wanted a way to study what happens to sculptures like David over time. The students built this machine, which they nicknamed Fred, and models that mimic the angle and pressure of David's ankles.
Essentially, our design created a machine that applied force downward until the models that we inserted in between these two plates were compressed enough where they broke.
This is the time, this is the total force, and we can see it just goes down as the model cracks.
David is made of marble, but the IPCH wants to study the effects of this pressure on multiple materials. So the group also made models out of concrete and clay.
It was definitely a really good experience getting to be hands-on so fast because it really let me see if it was something I wanted to do.
It's really satisfying to me because you see these students who, when they first showed up, they maybe didn't have any background in building things and making things, and now they're doing all this great stuff.
As for David, well, for now, he's still standing tall. Hopefully, with the help of research like this, he can stay that way.
With this infrastructure, it's important to look on the impact of individuals. Megan Perkins is one such individual. She came to Yale being certified to launch rockets and wanted to share that excitement with others. She created a small team, they wore the appropriate safety equipment, and launched a small rocket with the approval of the dean's office. After conducting this on Sunday, she showed up in my office Monday morning and said, "Dean, we'd like to launch big rockets." Megan, what is a big rocket? It's a little bit bigger than what we did before. She assembled her team and they launched not just one, but a number of rockets. And as the rockets would take off, they'd reach their apogee and then separate and come back down to Earth. In a specific challenge, the rocket also carried a payload of an egg. And the challenge was to see how that egg could return to Earth without the use of a parachute. Megan and her team designed a helicopter system and built that helicopter in the CEID. If you watch Megan's face as the egg is uncrated from its container and the vote of the judge that indicated the success of that mission. Again, this took place on the weekend, and on Monday she showed up back in my office and said, "Dean, we'd like to build really big rockets." And I said, "Megan, what is a really big rocket?" And she said, "They're pretty big." In this case, Thomas is 6 feet tall. The rocket is over 12 feet. Not only are they large in size, but their capability expands that of what we can launch on the East Coast of the United States and has taken Megan and her team into other areas of the country to launch their rockets. What's remarkable about Megan is with her single idea, how she was able to inspire and motivate others. Others such as Karl Marbach. Karl Marbach is the center on the Yale football team. Karl Marbach is also one of Megan's rocket team members. People such as Patrick on the right and Glenn on the left, who spent time at the Center for Engineering, Innovation, and Design building a rocket engine test platform. After graduating from Yale, Glenn ended up getting a job with SpaceX and Patrick with a company known as ABL Space Systems. The most amazing thing about Megan is her work inspired others, including the now 70+ members of the Yale Undergraduate Aerospace Association. Through innovation, Megan made an impact at Yale. Another example of innovation, impact, and products is Antonio Medina. Demonstrating the breadth, depth, and purpose of the Yale engineer, Antonio is also a musician, leading the Yale Precision Marching Band and also participating in the Yale Symphony Orchestra. His Yale experience included a summer in China, where he studied the language. The next summer, he traveled to Australia, not as a tourist, but as the conductor of the Yale Symphony Orchestra on the world stage. As an innovative product designer, one of Antonio's creations was a device to help the disabled. Using ultrasonic sensors and small microprocessors, he and a partner created a set of glasses that could be worn by the disabled, where the ultrasonic sensor would alert them to obstructions as they move forward using feedback that vibrated the glasses. They tested this with members of the disabled community, Philip and Hamrata, who took Antonio's design and gave feedback on its utility and needed areas of improvement. From sight to sound. Another creation by Antonio is a musical instrument using a small microprocessor and push buttons and an accelerometer, such that you not only touched the instrument, but your movement activated it. All elements of programming, electrical engineering, mechanical design, fabrication were required to create this new musical instrument by Antonio. And again, demonstrating the Yale shape engineered, he wrote the music and the instruction on how to play this brand new device.
The exhibition was like the laboratory of a musical mad scientist. The room was filled with strange-looking and sounding devices. I spoke with one inventor who described his invention.
So this is the Dyno, which stands for Directionally Nuanced Orbital. It's a MIDI controller instrument that allows you to play discrete pitches, but also allows you to affect the sound based on the motion sensors that are inside. So you can go.
One of the many users of this device has been the president of Sierra Leone, who visited the Center for Engineering, Innovation, and Design and was able to experience the joy of a new innovative product. Antonio's latest work is in the area of health, with this device being a tool created to help athletes. What it is meant to do is to use an optical sensor to indicate when an athlete has achieved the proper position in a squat. The device is first calibrated and then indicates through a beep every time a proper squat is achieved. Antonio's been working on this device, not only on the physical side, but also other utilizations for strength training, push-ups, and even high jumps. His work has focused on the electrical, electronics, programming, and also on the mechanical side. How do you create many units of this device in a short period of time? Here we see Antonio going from the music to the arts to athleticism, creating innovative products that help others. The impact, though, is not just on individuals, but also on partnerships. Two examples illustrate that. Yale has had its students associated with the field of competitive robotics on many platforms, including an organization known as FIRST Global, that assembles one team from each nation to come together in a form of the Robot Olympics, having done this in Washington, D.C., Mexico City, and in Dubai. Yale students participate by being mentors remotely for teams around the world, including those in Vietnam, Bangladesh, Germany, and Afghanistan. And then coming together at the events to meet their mentees in person. The team with Afghanistan developed a special relationship with Yale to the point that the team leader, Roya Mahbub, brought her students to the United States and visited the Yale Center for Engineering, Innovation, and Design. Roya has other interests beyond robotics, in that of providing platforms for young women to learn science and technology. With that challenge, Yale School of Architecture architects gathered at the Center for Engineering, Innovation, and Design and took Roya's ideas and designed a building to achieve that goal. They presented their results to Roya for her Dreamers Institute, a brand new facility located at the University of Kabul that would provide access to tools, education, and platforms for young Afghan women and men to learn technology in a totally awe-inspiring setting. As another example of the collaborations that are promoted through innovation, the pandemic brought together the Yale School of Medicine, School of Nursing, Engineering, and Public Health to take on the challenges associated with medical technology needs during the pandemic. This led to creation at the Center for Engineering and Innovation and Design, a site to evaluate the efficiency of face masks, both on their ability to remove particles in the airstream and on the impedance that they created for the flow. Other partnerships were made with local industry to design new forms of regulators using tooling that existed at companies such as Unilever, where the partnership led to new forms of injection molding and blow molded respirators. Working with physicians and technicians at the hospital, extending the use of ventilators, using engineering principles to monitor the distributed air, and then using the tools of 3D printing and manufacturing, how could some of these devices be produced locally? And how could they be produced in innovative ways within the local manufacturing sector? Those types of partnerships also extended into our classroom, where a class on computer-aided design studied airflow in a ventilator to understand how the effect of the design impacted the patients. Most importantly, what we see, though, I think, is the infrastructure, the individuals, and these partnerships, their influence on innovations at our institution. We've seen one example of the Center for Engineering, Innovation, and Design. That has been duplicated with our engineering labs by taking all of the disciplines and putting them in the same location to collaborate, learn from each other as they're doing their undergraduate lab work. And adding to that is the brand new SCI Center for Innovative Thinking at Yale, a facility in the heart of the School of Engineering that brings individuals from across campus to take on innovative challenges. So we've seen this approach duplicated and supporting innovation across the campus. That is an example of the Y-shaped engineer. One that has breadth in the social studies and humanities, one that has depth within the engineering disciplines and uses those skills to solve problems of purpose. Thank you.